After that last example, you may be questioning how practical it is to actually use elementary row operations to help us calculate the determinant of a matrix. And you'd be right. It's a long, laborious process. Now, I will say that, especially for large matrices, it can be useful to um, do a limited number of elementary row operations to make the matrix just a little bit easier to take the determinant of. Okay? But in a lot of real situations, you might as well just take the determinant right away instead of using elementary row operations. Where this idea really shines, though, is in more theoretical applications. So let's take a look at this lemma, and we'll take a look at a couple of these, and we'll be able to use what we know about elementary row operations to prove some of these. Okay? So let's let A be a square matrix, an n by n matrix. If A has a row of zeros, then the determinant of A is equal to 0. Now, we don't actually need elementary row operations to prove this one, though we could if we wanted to. So I'll do it a couple of different ways. So method 1, probably the simpler method. If we expand, or if we take the determinant of A, by expanding along the row of zeros, then clearly the determinant of A will be 0. Okay, what do I mean by that? If we take the determinant of a matrix with a row of zeros, okay, and we expand along that row of zeros, then our determinant would be, let's see, so we'd have 0 times the determinant of what's left, right? 1, 5, 4, negative 2. But do I really need to take the determinant of that? It's going to be 0 times something, right? And then I get another 0 time, and then if I cancel out the row and column that zero's in, I take the determinant of what's left. The 0 times anything is 0, so I'd get another 0. And same thing here. Cancel out row and column where that zero's in. If I take the determinant of what's left, well, I don't care because I'm multiplying it by 0, so I'll just get 0 again. Right? Anything times 0 is 0. So if I expand along the row of all zeros, I'm just going to be multiplying by a lot of zeros. So you take the signs into account, but negative 0 plus positive 0 plus negative 0 is still 0. Okay? So I just get a lot of multiplications by 0. The determinant is 0. Now, I did promise you another method. All right? Say the ith row of A is a 0 row. Obtain a new matrix B by multiplying row I by 2. So that is to get from A to B, I take the ith row, the row of zeros, and I multiply it by 2, and that's my new row I. That's an elementary row operation. Okay? Then from what we know about how elementary row operations affect the determinant of matrix B, my new matrix, is just twice the determinant of the original matrix A. right? Since to get to matrix B, I multiplied one of the rows by 2. But that row was the row of all zeros. But since the ith row of A has only zeros, after multiplying by 2, after multiplying row I by 2, we are left with the same matrix. Let me phrase it this way. Row I still has only zeros. Row I is still a row of zeros. Now, that's the only thing we did to get from A to B. We multiplied row I by 2, but nothing changed, right? Since row I has only zeros, 2 times row I is my new row I, but it's still the same row I. So my new matrix and my old matrix are the same. Which means determinant of B is also equal to the determinant of A. Plugging this into our previous equation gives us, so I'm going to plug determinant of A in for determinant of B. So the determinant of A is equal to 2 times the determinant of A. So if I just solve for the determinant of A by subtracting the determinant of A from both sides, I'll get 0 on the left. On the right, twice the determinant of A minus the determinant of A is equal to the determinant of A. So solving for the determinant of A gives us, so on the left-hand side, I get 0. On the right-hand side, I get determinant of A. Which is what we wanted to show. We wanted to show the determinant of A was 0. All right? Now, that's a lot wordier than our first method, right? I just wanted to give you a peek of it. I thought it was a cute method. Okay? For part B, that's the more interesting one here. And we're going to use what we learned in part A to prove part B. So for part B, we want to show that if 2 rows of matrix A are the same, then the determinant of A is 0. Okay? So let's pick which 2 rows. So suppose row I and row J in matrix A are the same. Obtain matrix B from matrix A by applying the elementary row operation negative Ri plus Rj is the new row J. Okay? Then what's matrix B look like? Well, if row I and row J were the same in matrix A, and I just took row J and subtracted row I, that means the new row J in the new matrix B should be a row of zeros. Then row J in matrix B is a row of zeros. Okay, and what do we know about matrices with a row of zeros? If a matrix has a row of zeros, then the determinant of that matrix is 0. Meaning the determinant of B equals 0. Since we obtained matrix B from matrix A by adding a multiple of one row to another row, okay, how does that affect the determinant again? If we add a multiple of one row to another row, how does the determinant change? Well, actually, it doesn't, right? Remember, for this particular elementary row operation, the determinants are equal. So since we obtained B from A by applying this elementary row operation, the determinant of A must be equal to the determinant of B. And we already saw that since B has a row of zeros, the determinant of B must be 0. Okay? And that proves part B. We have 2 rows of A. If 2 rows of A are the same, then we've shown the determinant of A is equal to 0. For part C, you're going to approach it very similarly. If you could show that that we are applying an elementary row operation to matrix A, or to a matrix to, let me rephrase. If we could show matrix A is an elementary row operation of one of the matrices that we've already discussed here, then you can use that to find the determinant of matrix A. I'm going to leave part C for you to do.